You ever see something and think, wait, is that a real pattern or just a random fluke? It happens all the time, right? Well, scientists actually have a tool for this. It's kind of like being a detective for data. And today, we're going to learn exactly how it works. Okay, so let's put ourselves in the shoes of a marine biologist for a second. Imagine you're out on a protected reef, and you notice the fish just seem bigger, like way bigger than the ones in the area right next door where fishing is allowed. Your first thought is, yes, the protection is working. But then the doubt creeps in. How do you know it's real? How can you be sure you didn't just get lucky and happen to see a few big ones? Is it a real difference or just random chance? And that right there, that is the core challenge, not just for our biologists, but for researchers everywhere. We need a solid, evidence-based way to separate a real, meaningful pattern from just, random noise. This is how we figure out if a new medicine is actually saving lives or if a big policy change is really making a difference. So, how do we do it? Well, the logic starts with an idea that's probably really familiar to you from every courtroom drama ever. Innocent until proven guilty. It's a powerful concept. And in statistics, we do something very similar. We don't jump in trying to prove our awesome new ideas right. No. We actually do the opposite. We start by assuming our idea is wrong. This starting assumption has a formal name. It's called the null hypothesis. You'll see it written as H0 or H0. Think of this as the default setting, or the ultimate skeptic's position. It's the nothing to see here, folks hypothesis. It basically says there's no effect, no difference, no relationship. So for our fish example, the null hypothesis would be that the average fish size is exactly the same in both areas. Super boring, right? That's the point. So you can see here, we set up two competing ideas. On one side, you have the null hypothesis, H0, saying there's no difference. And on the other side, you have the alternative hypothesis, HA. Now, this is the one we, as the researchers, are actually excited about. It's our hunch. It's the claim that there is a difference. And our whole job, our mission, is to gather enough evidence to be able to throw out that boring old null hypothesis. Okay, so that brings up a huge question, right? How much evidence is enough? How weird or surprising does our data need to look before we can confidently say, nope, we're rejecting that null hypothesis? This is where statisticians literally draw a line in the sand. And getting this right is a big deal. It's what decides if a new drug gets approved or if a scientific discovery is taken seriously. And that line? It gets drawn on this thing right here, the normal curve. You've probably heard it called the bell curve. It's this really elegant, symmetrical shape that pops up everywhere in nature. Think of it as our map. The big hump in the middle, that's where all the common, expected stuff happens. But way out on the edges, in those skinny little tails, that's the rare stuff, the surprising stuff, the outliers that make us go, And there's a really handy rule of thumb for this curve. It tells us that about 68% of everything falls really close to the middle. That's the super common stuff. About 95% of all the data is considered likely, falling within a certain range. That means only 5% of stuff is left over for those weird, eyebrow-raising results way out in the tails. And that 5%, that's going to be really important. This leads us to one of the most famous and maybe misunderstood ideas in statistics, the p-value. The best way to think about it is as a fluke-o-meter. It's one single number that answers a very specific question. If the null hypothesis is actually true, if there's really nothing going on, what's the probability we'd see results like ours just by pure dumb luck? So a really, really small p-value means, whoa, this would be a massive fluke. And a big p-value means, this could totally happen by chance. And here it is. This is our line in the sand. In most fields, from medicine to psychology to biology, that line is drawn at 0.05, or put another way, 5%. This magic number is called the significance level, or alpha. And what's crucial is that we decide on this number before we even look at our data. It's the rule we set for ourselves ahead of time. It's our official definition of what counts as surprising. So the rule is simple. If our p-value, our flukometer reading, is smaller than our 5% cutoff, we get to declare our result statistically significant. This is the moment we've been waiting for. It means we have enough evidence to finally say we reject the null hypothesis. This is the statistical green light. It's when scientists get to say, hey, I think we found something real here. All right, that's enough theory for now. Let's make this real. We're going to walk through an actual case study, step by step, to see this whole process in action. Get ready for the skink showdown. So here's the setup. Researchers are out on these islands, and they notice something. The skinks, these little lizard-like critters, from a place called Round Island, just seemed bigger than the ones from a neighboring island called Gunner's Quinn. And the question is the exact same one our marine biologist had. Is this a real biological difference between the two populations, or did they just get lucky and happen to catch a few big ones on Round Island that day? To find out for sure, we can't just guess. We have to follow a clear 4-step plan to get our verdict. Step 1, state the hypotheses. Step 2, figure out our analysis plan. Step 3, actually crunch the numbers on the data we collected. And step 4, the big finale, interpret the results and make a call. Okay, step 1, let's state our hypotheses. First, the null hypothesis, the nothing is happening view. That would be, the average skink length is exactly the same on both islands, no difference. Then we have the alternative hypothesis, our hunch, and that is, nope, the average skink length is different. So, the researchers go and run the right statistical test for this job. It's called a t-test, which is perfect for comparing the average of two groups. And after all the math is done, it spits out one single important number. This number is our key piece of evidence. It's called the test statistic. And for our skinks, that number is 3.56. So, is 3.56 a big deal? Is it surprising? On its own, the number doesn't mean much. We have to compare it to something. We need to compare it to that line in the sand we talked about. For this specific test, we can look up a number in a table, and this number is called the critical value. It's basically the hurdle our evidence has to clear. And for this showdown, that hurdle is set at 2.262. And this is the moment of truth. We just compare the two numbers. Our evidence is 3.56. The hurdle we had to clear was 2.262. While 3.56 is way bigger than 2.262, our evidence didn't just clear the hurdle, it soared over it. This means our result landed way, way out in that surprising zone on the curve. It's a result that would be incredibly unlikely to happen just by random chance. And because of that, we can now deliver the final verdict. The difference in the size of these skinks is officially statistically significant. We have gathered enough evidence to reject the null hypothesis. We can say with statistical confidence that, yes, the skinks on Round Island are indeed a different size. Case closed. So that's pretty cool, right? We solved the skink mystery. But obviously, this whole powerful process isn't just about lizards. So let's zoom back out for a minute and talk about what this tool really means for all of us. One thing to always remember is that this process is based on probability, not 100% certainty. So it's possible to make a mistake. There are actually two kinds of errors you can make. A type 1 error is a false positive. It's like the data tricked you, and you convict an innocent person. A type 2 error is a false negative. You miss a real effect, and you let a guilty person walk free. That 5% significance level we talked about, that's us deciding we're willing to live with a 5% risk of making that first kind of error, a false positive.
So when you boil it all down, why does this matter so much? Because hypothesis testing is one of the absolute cornerstones of science and smart decision-making. It gives us a reliable way to filter out the random noise from the real signal. It forces us to use hard evidence instead of just gut feelings or one-off stories. It's how we find out, for real, if a new drug works, if a teaching method is effective, or if a conservation strategy is making a difference.
And that really brings us to a final thought for you to take away. This whole framework, it's not just for scientists and lab coats. It's a powerful way of thinking critically about the world around us. So the question I want to leave you with is this. What's a big assumption you have in your own work, or even in your life, that could benefit from being put to the test?